this video, I'd like to look at some data of a cart on an incline and use it as an example in Excel of fitting to a polynomial and calculating the percent error and so on. So just here's the scenario. We have this cart rolling down an incline. The incline is at some angle theta from the horizontal, from the level. And we have some sensor measuring, in this case, it's the position of the cart as a function of time. Okay, so that's the scenario. So we had 3 different heights, so 3 different angles, and we want to sort of analyze this data. So the first thing we're going to do is make a plot of position versus time. So that has position versus time is time in the first column, so that'll be on the X, and position in the second column, so that'll be the Y, and that's the order in which I want them. And make an XY scatter. And then we see that we had some nice smooth parabolic data, which is what we're expecting, and then something else happens. This is sort of like the cart hitting something at the bottom of the incline and sort of bouncing back. And so we're not interested in that part. We want to have, our analysis wants to be sort of freely flowing cart down the incline. So we want this first part. We don't want anything. We don't want this sort of second half. Now we can take 2 approaches. I already have a graph with this sort of bad data in it. So 2 approaches I can take. One is to sort of re-highlight the data and sort of stop highlighting at the point that where the bad data starts coming in. Or I can, if I don't want that bad data at all, if I'm willing to get rid of it, then I can just go ahead and delete it. So that's what I'm going to do, the delete approach this time. So I'm going to go, let me go up to this highest point, 5.49. So it's giving me, if I point at the dot, it's telling me the X and the Y, and the X here is a time. So I'm looking for a time of 5.49. And I don't, that's the point where after which I want to delete. So here's my 549 or 54862. And after that, I want to delete. So I'm going to highlight this and click my delete key. And it updated my graph. So I have one slightly little hinky point here, but I'll keep that. Okay. I'm going to highlight my chart. That makes this chart design and format come in. I want the chart design. And I want quick layout number 9. And the physics theory says that this should be a polynomial. So I don't want to fit it to a straight line. I want to fit it to a polynomial. So I'm formatting the trend line and choosing the polynomial. Don't want this legend. The x-axis here was time in seconds. The y-axis was position in meters. This was, I'll say cart incline, and it was, I don't know, my first trial, so I'll say trial 1. And I'm going to move this. I have the equation I want, polynomial. I'm going to make it a little bit bigger. So home, font size, raise it up a bit. Move its position. Okay, the r squared is good. It's close to 1. So this form fits the data pretty well. And now I want to compare it to this theory and sort of extract the quantity I want, which is going to be acceleration. So here's this bold equation here is the theory that there's some polynomial in time. Now Excel calls it X, but I know it's on my x-axis as time. So if I wanted to, I could edit this and go in there and change these X's to T's, but I'm not going to, but just realize Excel doesn't know that this was time until I wrote time. So it just always calls what's on the x-axis X. But in the theory, in physics, we know it's time and we call it t. Okay. The order is reversed from like the equation Excel gave to the equation we know from physics, but that hardly matters. The order doesn't matter. But the acceleration is involved with the square term. So I've got to compare square term to square term. And I have to remember that what Excel called x, physics is calling t. So x squared is t squared. And then in the comparison, what I get from Excel is, other than x squared, is 0.0517. And what is left, what's other than t squared in physics, is a divided by 2. So a is not 0.0517. A on 2 is 0.517. So I have to multiply the 0.0517 by 2 if I want to get a. So again, the coefficient of t squared is the acceleration divided by 2. So the 0.0517 is acceleration divided by 2. So acceleration is 2 times this number. So I'm going to say, here's the experiment, and I'm going to let Excel multiply by 2 for me. I don't know. So equal 2 times 0.0517. And I should say that that was meters per second squared is the unit. If the y-axis is meters and the x-axis is seconds, then this quantity I'm going to multiply by seconds squared, and I want to get meters. And the quantity that you can multiply by second squared and get meters is meters per second squared. Okay, what else do we want to do here? Then we want to do the theoretical. Okay, so the angle here is 0.289 degrees, and the theory says that this is the acceleration due to gravity, g, 9.8, times the sine of the angle. But one thing you have to watch in Excel is that its sine works in radians. So we can't just put in sine of this, we have to get the radians. So let's do it in 2 steps. So I'm going to insert a column here. I could do it in 1 step, but let's break it down. Let's say angle in radians. And then we can say sort of there are 360 degrees around a circle, and that corresponds to 2 pi radians. So we could like do that sort of ratio for ourselves, but Excel has a function. So let's make Excel do the work. So there's a radians function, which will convert angles in degrees to angles in radians. So here is the angle in radians using the radians formula of Excel. And then here is the formula is G, which is 9.8. You want 9.81, feel free, times sine of the angle in radians. Okay, so here is my theoretical acceleration. Again, I should put in meters per second squared for a unit, and then a percent error. So this percent error is experiment minus theory, that whole thing divided by theory, and then express that as a percentage. And Usually we take an absolute value. Okay. Let me build up slowly. And so first I want experiment minus theory. Okay. So that's not percent error yet. I'm building up. I want to divide that by the theory, but I want to divide all that by the theory. So I need parentheses. So I'm going to put parentheses and then divide by the theory was P3. Oops, that was not a parenthesis. There's a parenthesis and then divide by P3. So that is closer to what we want. We have the experiment minus the theory divided by the theory. I've seen it occasionally where people will leave it with a sign to know whether it was sort of positive or whether the error was positive or negative, but most often you tend to see it with a more absolute error sort of. So there's a formula in Excel, ABS for absolute value. So let's put that around our expression here. Okay, and then it's a percentage. So there are sort of two possible approaches in Excel. One thing you'll see, like if you look up formulas, say on the internet or in lab manuals, what have you, they'll usually multiply by 100. So if you're sort of doing it by hand, that's how you will sort of express it as a percent. But what you can do in Excel is just format this as a percent. And so you can come here to this percent style and click that. And then that does the multiplying by 100. But it doesn't change the number in the cell. The number in the cell is still that calculation of 0.27, but it's just, so it doesn't multiply by 100. It's not the same as what people are doing, you know, by hand. You don't multiply it by 100. You just make it look like you have. It's a formatting. It's a style thing. And that's more or less it, other than sort of doing it 2 more times, which I think I will skip out on here. I've shown you what I wanted to show you in Excel here. Thanks for your attention.